So on page 97, the first example, and it's got a few different parts to it, but I mean the whole page is the example, but you'll see. The function defined by f of x equals 1 over 1 minus x. Write the Maclaurin series. All right, we're kind of familiar with this at this point because we're looking at something that is geometric in nature. All right, so from there we can match this up, and it's tailor-made, pun intended, of course. So a sub 1 over 1 minus r. All right, because remember, power series, they have that's the umbrella topic that also contains Taylor series and Maclaurin series. So Maclaurin and Taylor are special cases of power series. All right, so from here I would be saying that a sub 1 is equal to 1 and r is equal to x. All right, so my series would be n equals 1 to infinity. All right, so 1 times x to the n minus 1 power. All right, so that's power relation, so we're in pretty good shape. All right, the first 4 non-zero terms. So plug in a 1, you get a 0, so this becomes a 1, 0 exponent, so it becomes a 1. Plug in a 2, we're going to get a clean x. All right, plug in a 3, you're going to get an x squared. So the progression gets us to an x cubed and so on. All right. We already know the general term, but I'm going to write it without the 1 just for giggles. All right, and so for what values does the series converge? Because we know that it is geometric. Now it follows the Maclaurin progression in a sense, but it is geometric. We can say the absolute value of x is less than 1, which means that x is between -1 and 1. All right. So we have that taken care of. Use your answer to A to find the Maclaurin series. And really, I mean, it's kind of iffy as to why, it's centered around 0, so it's a series that's centered around 0, so that makes it Maclaurin, but we could just call it a power series and be done with it, just to be clear about that. All right, so if I want f prime, so this whole thing is f prime, we learned on the previous page that I can take the derivative inside the summation, around the summation, but I could also take it term by term. All right, so multiply the power by the coefficient, n minus 1, reduce the power by 1, n minus 2. All right, differentiate each individual term. 1 goes to 0, irrelevant. X goes to 1, then we have a 2x, then we have a 3x squared. I'll put a 4th term there just because, we did before, so, and also they told us to. Just because we don't have a term to differentiate to give us that 4th term doesn't mean we should neglect it. And again, of course, the nth term, or the general term. And I'm just going to do a copy-paste job here. All right, so where does it converge? So this is my interval, again, interval of convergence. All right, now if you look at it and compare, I didn't want to resize, copy. If you compare the common ratio for part A to the common ratio in part B, you see that nothing changed. It's still centered around 0. So why would the interval of convergence change? It won't. So when we're tackling part C, it has to relate to part B in some capacity, otherwise the directions wouldn't state it as such. Looking at what I see here, one thing that I know that I could do is I can rewrite it. That's always an option. So I'm going to rewrite it as 1 over 2 times a third, because those denominators of 3, 9, 27, that's geometric in nature. It's telling me that I'm multiplying by, I'm increasing my coefficients, but I'm multiplying by a 1/3 consistently. So if I rewrite this as 3 times 1/9, 4 times 1/27, and then take that additional step of saying 1 plus 2 times a third plus 3 times 1/3 squared plus 4 times 1/3 to the third, then take the extra step of grabbing my work up from up here, bringing it down, matching it up. I'll change the color so it's a little bit more obvious. You can see it's following the same form, but only when x, so dot dot dot, when x is equal to 1/3. I almost said 3. When x is equal to 1/3. All right. So now we can backtrack a little bit and say, all right, so this must be the derivative of the original function f of x. Which in turn is going to be negative 1 minus x to the negative second times a negative 1. All right, specifically, it's the derivative when x is equal to 1/3. Now, since x falls into the interval of convergence, we know that these two things are going to go hand in hand with one another. So if I recognize this series as the expansion, an appropriate expansion of the function, then I can conveniently differentiate one way or the other. All right. So I would just be looking for f prime of 1/3, negative 1 minus 1/3 to the negative second times a negative 1. Those two negatives will cancel. Could have done that already. All right, so that's 2/3 to the negative second. Reciprocal, 3/2 squared, 9/4. And so that would be the sum of my series. All right. The other way, so we're integrating now, but first we have to account for the fact that it's f of t. So instead of 1 over 1 minus x, it's 1 over 1 minus t. All right. But we can take our full-blown expansion and hang on to that. We're just replacing all of the x's with t's. So it's a power relation. So we're going to increase our exponents by 1, divide by the new exponent. All right, so using this idea, the sum from n equals 1 to infinity, the n minus 1 becomes an n. So 1 over n t to the nth. So t plus 1/2 t squared plus 1/3 t cubed plus all that good stuff. All right, so 1/4 t to the 4th plus da 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 da. We know the nth term, 1 over n t to the nth. All right, that's equivalent to, again, the antiderivative of f of t, feet? No, f of t dt. So now what I want to do is evaluate that over the interval of 0 to x. All right, so if I do that, well, actually, let me save that for another step. You think about what would happen. Every term has a t in it, so I'm going to replace every term with an x, then replace every term with a 0, and it's basically going to zap away anything that's got a 0 substituted in for t. So we're going to get pretty much back to where we would expect to be had we worked with x all along. But this gets into the idea that you'll explore more in Calc 3 involving changes of variables. All right. So we're in good shape now. Now, you could have also kind of gone a different way. I'm going to kind of move some things around here. You could have started with a fresh new series to represent the antiderivative, not antiderivative, the function to be anti-differentiated, and then gone from there. So if you had gone with an initial assumption of a power relation, you might have said something like t to the nth. You know, that's another way of representing a geometric relation, in which case you'd have an n plus 1 as a result. Either way is fine. All right. So for what values will the series converge? Well, it's still geometric, so it's still going to converge over the interval of -1 to 1. All right. So it really just begs the question of whether or not the -1 is going to be okay versus the +1. All right, because, you know, I'll just kind of go back and refresh our memories here. You cannot gain an endpoint by differentiating. We've already taken care of that. You cannot lose an endpoint by integrating. All right, so we're not worried about losing an endpoint because we never had them to begin with. But it doesn't say anything about retaining an endpoint or gaining an endpoint, which are possibilities. So we have to account for that. And the way to account for that is by testing them. All right, the possible endpoints, as we know, the interval convergence previously was this, but now what I'm going to do is I'm going to test x equals -1. All right, so that's going to be the sum from n equals 1 to infinity of, I'm going to write it as, we're replacing the x with -1, so -1 to the nth over n. All right, so this is alternating series. All right, it is decreasing. All right, we don't have to be explicit with that. Sometimes just common sense. All right, because if you look at it and say, well, if I removed the -1 to the nth, it would just be 1 over n, 1 over 1, 1 over 2, 1 over 3. The only time I need you to include a demonstration is if I say I need you to include a demonstration. All right, show that it's decreasing, but you can expect that I won't be asking you to do that. All right, so then I would look for the limit as n approaches infinity of 1 over n. That's equal to 0, and so that means that this converges. All right, so we have a converging situation here. Now I'm going to test, so we gained an endpoint is what I'm saying. X equals +1. So the sum from n equals 1 to infinity, so I'm plugging in a 1 for x, 1 to the nth is 1, so it's 1 over n. This is a p-series situation, so it diverges by the p-series test because the p-value is equal to 1. All right? It needed to be between 0 and 1. All right? So our interval of convergence, this is work in progress here, just gained a little inequality and a little extra to its inequality that it didn't have before. So the -1 is now part of the set. All right. Now, just like part C, part E is asking us to use D to answer. I'm sorry, I've almost said it incorrect. I almost corrected myself to the incorrect answer. All right. Use D to help with E. So I'm going to rewrite this as 1 times 1/3 plus 1/2 times 1/3 squared plus 1/3 times 1/3 cubed, and hopefully you start seeing the relationship 1/4 times 1/3 to the 4th, and so on. All right, so it's telling us, if we look at it, that what we're up against is in the same form as the antiderivative of f of t dt over the interval of 0 to x. All right, but specifically where x is equal to 1/3. All right, so when x is equal to 1/3, we would then say, all right, I see what you're after here. Find the antiderivative over the interval of 0 to 1/3 of f of t, which is going to be 1 over 1 minus t, which I'm going to write as 1 minus t to the -1st power. And for that, it's up to you. You could do it right in a calculator. It's a definite integral. Or you could do it by hand. Either way. If you do it by hand, it's a little bit of a baby chain rule situation, but that's up to you. I'm going to go calculator math 9. One minus back to x, right? Raised to the -1st. Oops, I put a minus. -1st dx over the interval of 0 to 1/3. So it's got a little fundamental theorem of calculus going on here. Let's see if I can math frac that. So about 0.405. All right. If you want to, again, you could say, if you wanted to do it by hand, increase the exponent by 1 minus t to the, actually 1 minus t, geez, what am I thinking of? This is natural log, ln 1 minus t, then correct for the derivative on the inside, so negate it over the interval of 0 to 1/3. So negative ln 1 minus 1/3 would be 2/3 minus negative, so plus ln of 1, which is going to 0 anyway. So negative ln of 2/3, and that's the course.